Contingency analysis to evaluate power system security and voltage stability. For the critical buses. Using Powerworld simulator. Abstract. This paper presents different contingency ranking and screening methods using linear sensitivity factors for the faster response of the system operators to estimate the post-contingency active power flow for all the system transmission lines. The study depends on the Powerworld simulator to investigate the single contingency scenario and rank the most critical lines using different formulas of performance indices. Then, by applying the multiple contingency scenarios using the bus outages, an investigation was performed using the complex power performance index to specify the critical system substations that could happen because of any such missile attack on the critical substation or for any natural reasons such as earthquakes, hurricanes, floods, etc. Finally, evaluate the critical bus's voltage stability using PV and QV curves and assess the system stability under the highest pi contingency. Keywords: contingency ranking, contingency screening, linear sensitivities, multiple contingency analysis, performance index, voltage stability, PV curves, QV curves. Introduction. System security entails methods aimed to keep the system running when components fail. The most typical failures in power systems are transmission lines and generating units. Transmission line failures affect power flows and bus voltages on the other lines. When a generator goes out of service in the power system, the operational conditions of the transmission lines and other generators, such as the system frequency, active and reactive power flow. 1-2. Planned outages as well as forced outages of transmission lines and generating units change the topology of the power system. As such, their impacts on the power system should be analyzed and rank the severity to take the proper action to maintain system reliability and keep customer satisfaction. 3-4. The main concern of power security is to sustain the flow of energy from the producing power plants to the load center, local customers. However, the design of a power system should meet a certain degree of reliability, adequacy, quality, and security. To overcome the dynamic interruptions which might be distributed minor failures or major localized interruptions. 5. Power systems that operate with a single outage or failure scenario are usually considered secure. If such a circumstance occurs, the widely used term N1 indicates that the system will stay in a secure working condition. So we need a fast methodology like sensitivity factors to examine the single element outages to rank and screen the less severe failures to evaluate the remaining using AC power flow or applying multiple outage NK. 6-7. The new advanced software such as Powerworld provides a wide range of functions for power flow, security analysis, system stability, and other complete packages that can help researchers in their work, as illustrated in Figure 1. After investigating the IEEE-14 bus using the Powerworld simulator, we find that line 10, bus 5, bus 6, is the most vulnerable line by applying the N1 scenario, and the substation represented by bus 2 is the most critical node in the system from the voltage stability point of view. 2. Contingency analysis for power systems. Power system reliability takes priority in power system operations, particularly in large interconnected computerized power systems where widespread blackouts are a possibility. A power system should design to meet reliability requirements and operate economically. 8. Power systems are huge, interconnected components that might collapse due to internal or external reasons, such as a circuit breaker malfunction or a severe weather situation. Transmission lines and generating units are the most common failures in power systems. Transmission line failures affect power flows and bus voltages on the other lines. Contingency analysis procedures. Contingency analysis examines which transmission line or generator failure will result in a violation in line flows or bus voltages. To estimate system states, contingency analysis analyzes single and multiple outages. In the contingency analysis, the line flows and bus voltages are compared to their limitations. Contingency screening, also known as contingency selection, is a technique in which the critical contingencies are picked using a DC power flow, and then the chosen contingencies are completely analyzed using an AC power flow. 9. 1. Linear sensitivity factors. Linear sensitivity factors LSFs are calculated using C-flow analysis, which ignores bus voltages and MVA flow and estimates the MW flow in each branch with a 5% accuracy. 10. To evaluate the critical cases by formulating a method to rank the contingency scenarios in such a manner that only those that are likely to result in limit violation need to be investigated in more depth, while the others are neglected. 11. These LSFs represent the expected change in the transmission line flows due to a change in generation or network configuration. These variables can be obtained using many techniques, but they are mainly categorized into two categories. Generation shift factors, GSF. The generator shift factors explain how the active power flow on transmission line L changes when the power generation unit at bus I disturbed as shown in equation 1, equals dash 0, 1, where represent the change in power flow of line when the generation at bus I got out of service equals dash 0 and the new power flow on each line in the network could be estimated as follows. 1 equals 0 dash, 0, 2. The outage flow, 1 on each line can be compared to its limit, and those exceeding their limit announced as ovulation. This would tell the operations personnel that the loss of the generator on bus I would result in an overload on line L11. Line outage distribution factors, LODF. Line outage distribution factors, LODFs, calculate the line active power flow changes when the line outages take place in a power system, as shown in equation 3, equals dash 0, 3, where represent the change in power flow on line when the line I got out of service equals dash 0 and the post contingency power flow on line L with line K failure can be estimated as follows. 1 equals 0 dash, 0, 4. For real-time security analysis, the impacts of hundreds or even thousands of outages on lines flows and bus voltages must be examined. This depicts the reality need for the speed, accuracy, and acceptance of solution technique. In reality, solving with full AC power flow is not feasible for all contingency scenarios. Because the large number of these contingencies do not result in severe generation shifts or transmission lines violations. The objective is to eliminate the major part of harmless scenarios from the short list of branch contingencies. 10. 2. Performance indices. The System Performance Index, PI, is a tool that could be used to estimate a contingency's relative severity. System performance indicators aren't all the same, and they take on various forms based on the criteria that concern most to the operator. However, physical elements of the system should be considered while choosing a performance index type. 8. The most commonly type of system performance indices used as a measure of how much system variables like bus power injection or bus voltage differs from their rated values. For the PI, several relations have been proposed. The values we're interested in are used to choose which PI relationship to use. The following are the most common PI types. Active power-based ranking methods. The Active Power Performance Index, PIMW, gives a measure of line power flow overloads. It is given by the following equation. Equals 1, 2 where, 5. Post-contingency active power flow in line L. Lim active power capacity, limit, of line L. Weighting factor of active power limit violation. This index ranks the contingencies that result in a large number of heavily loaded and overloaded lines in the system over those that result in a few lightly loaded lines. Reactive power or voltage security-based ranking methods. The Voltage Performance Index, PIQV, is a technique used to measure bus violations and evaluate system inability resulting by out of limit bus voltage. It can be calculated as follows. equals dot, equals 1, dash, lim, where, 6. Post contingency voltage at bus I. Lim bus voltage limit. Weighting factor of voltage at bus I. This index ranks the contingencies that result in a large number of violated limits. Bus voltage, could be over voltage or under voltage, in the system over those that didn't exceed the nominal bus voltage. 3. Powerworld simulation for single contingency N1 scenario. In this chapter, we will investigate the contingency analysis for the IEEE 14 bus system using the Powerworld program. The base voltage and power are considered as 138 kV and 100 MVA respectively. For the base case situation, the total generation is 285 MVA, 272.4 plus J82.4, and the total load is 269 MVA, 259 plus J73.5, and the spinning reserve in the system with losses. The dynamic transient is 16 MVA, which represents 7% of the largest generation unit located on bus 1. After build the system and obtain the base case result for the lines and buses, and then perform the contingency analysis using DC and AC power flow analysis using Powerworld simulator under single line lowest scenario, the simulator report that the DC power flow have a total runtime to complete the contingency analysis is 0.21 SEC compared to 0.35 seconds for AC power flow as shown in figure 1, below. A.N1 DC contingency analysis results. By applying N1 contingency analysis using the D power flow analysis as illustrated in Appendix 1, the performance indices calculated separately for each case as shown below in Table 3. As per the result form, DC power flow, line 10 had ranked as the highest power flow performance index, indicating that this line is the most critical contingency in the system with 5 overloads. Line N largest, pi equals 12.17, then line 1 outage which overloads 2, then line 3 outage with 1 overload, and last line 2 with 1 overload also. B.N1 AC contingency analysis results. By applying N1 contingency analysis using the A power flow analysis as illustrated in Appendix 2, the performance indices calculated separately for each case as shown below in Table 4. Using AC power flow, again line 10 has the highest power flow performance index, indicating that this line is the most critical contingency in the system with 6 overloads. Line N largest, pi equals 13.6, then line 1 outage which overloads 2, then line 3 outage with 1 overload, and last line 2 with 1 overload also. As noticed, the use of DC load flow models provides acceptable capabilities for the critical contingencies ranking. And for wide range systems, where the voltage amplitudes may not be a major problem, and the DC load flow provides appropriate accuracy in terms of active power flows and ignoring the reactive power flow and transmission line losses. 4. Powerworld simulation for multiple contingency NK scenario. In this section, I will extend the study of contingency analysis to cover more outages or failure events at the same time, and I will continue the investigation for the bus outages that could happen because of any such missile attack on the critical substation or for any natural reasons such as earthquakes, hurricanes, floods, etc. A. Multiple contingency ranking. After performing the contingency analysis for each bus outage, which represents simply the multiple contingency scenarios, where each bus connects at least 2 elements in the system, I proceed the critical bus ranking using new developed performance index combines the active and reactive performance indices represent early in section 2. As shown in equation 7 below. Equals V 2 plus 2 7. Where, as result, for the different effects of the bus outages when we monitor the transmission line power flow and calculate the active power performance index in table 5, we conclude that the most severe outage occurred when the bus 2 substation got out of service with PIMW equals 19.44 due to 3 lines overloads, then bus 5 outage with PIMW equals 13.77 due to 8 lines overloads. But consider the bus voltages for the remaining buses and calculate the voltage performance index in table 6, it's observed that the severe outage occurred when the bus 6 substation got out of service with PIQV equals 2.84 due to 2 buses goes under voltage limits, then bus 5 with PIQV equals 2.60 due to 4 buses goes under voltage limits. Finally, to determine the most critical and sensitive bus, by applying the complex performance index represented in equation 7, as shown below. As a conclusion form table 7, we notice that the most severe outage affecting the system drastically and leading to a blackout is the outage of bus 2 with PI complex equals 19.44 due to 3 lines overloads, 1 bus going under voltage limits, and other 7 elements going out of service as shown in figure 2. Also, we can notice the performance index ranking procedure is totally independent to determine the critical cases regardless the number of disturbed element nor exceed the limits. B. Critical bus PV curve. In this section, I will investigate the system stability using PV curves for the critical buses and the operating zone effects for each of the buses if we apply a single contingency analysis. Figure 4 illustrates the PV curves for the most critical buses obtained before as shown below. Figure 4. PV curves for the critical buses. A picture containing graphical user interface. Description automatically generated. Following the implementation of the PV curve analysis for the critical buses, I chose the top 3 critical line contingencies and notified the drastic shrinking in the operating zone, as well as the significant reduction in maximum power capacity. Such a line 10 outage will reduce the voltage tolerance to less than 2% at 100 MW power transfer. After that, the bus voltage will collapse and lead to a system blackout, as shown in figure 5, where the voltage tolerance was around 10% and the maximum power transfer exceed 300 MW. Figure 5. PV curves for bus 2 and the highest pi contingency. Text. Description automatically generated with medium confidence. Similarly, we can generate the PV curve for all critical buses and conclude the maximum active power transfer during the top rank single contingency using the different types of performance indices. Figure 6. PV curves for bus 5 and the highest pi contingency. Text. Description automatically generated with medium confidence. Again, for bus 5, the line 10 outage will reduce the voltage tolerance to less than 2% at 100 MW power transfer, as shown above in figure 6. However, for bus 6, line 2 outage will reduce the voltage tolerance to less than 8% at 100 MW power transfer, as shown in figure 7. Figure 7. PV curves for bus 6 and the highest pi contingency. Text. Description automatically generated with medium confidence. Finally, for bus 4, line 10 outage will reduce the voltage tolerance to less than 6% at 100 MW power transfer, as shown in figure 8. Figure 8. PV curves for bus 4 and the highest pi contingency. Text. Description automatically generated with medium confidence. C. Critical bus QV curve. In this section, I will investigate the system stability using QV curves for the critical buses and the operating zone effects for each of the buses if we apply a single contingency analysis. Figure 8 illustrates the QV curves for the most critical buses we obtained in previous section for multiple contingency ranking. Figure 9. QV curves for the critical buses. Following the implementation of the QV curve analysis for the critical buses, I chose the top 4 critical line contingencies and notified the voltage tolerance in the operating zone, as well as the sensitivity factor, dQ/dV, which notifies us of the allowable modification in the reactive power injection to the available voltage variance, as represented below table 8. As shown in figure 10, from bus 2 point of view, a line 1 outage will reduce the voltage tolerance to less than 16% and increase the reactive power injection to keep the system under stable condition with very little dQ/dV equals 1%. And if the required injection increases further, the bus voltage will collapse and lead to a system blackout. Text. Description automatically generated. Similarly, we can generate the QV for bus 4, a line 1 outage will reduce the voltage tolerance to less than 17% and increase the reactive power injection to keep the system under stable condition with very little dQ/dV equals 2%. Figure 11. QV curves for bus 4 and the highest pi contingency. Text. Description automatically generated. Also, for bus 5, a line 1 outage will reduce the voltage tolerance to less than 17% and increase the reactive power injection to keep the system under stable condition with very little dQ/dV equals 2%. Figure 12. QV curves for bus 5 and the highest pi contingency. Finally, for bus 6, a line 1 outage will reduce the voltage tolerance to less than 14% and increase the reactive power injection to keep the system under stable condition with very little dQ/dV equals 1%. Figure 13. QV curves for bus 6 and the highest pi contingency. Conclusion. This paper is representing the different contingency ranking and screening method using linear sensitivity factors GFD and LODF for faster response of the system operators to estimate the post-contingency active power flow for all the system transmission lines. And the major of the study depends on utilizing the built-in function for the Powerworld simulator to investigate the N1 contingency scenario and ranking the most critical lines and buses using different formulas of performance indices, and finally evaluate the critical bus's voltage stability using PV and QV curves and assess the stability under the highest pi contingency. 6. Acknowledgement. The authors gratefully would like to acknowledge the support and help that have been provided by King Abdulaziz University.